In general chemistry, you probably also made calculations about kinetics. And so kinetics answers for us the question about how fast a reaction might be. We think about it the same way, of course, in organic chemistry. And so let's go back to our hypothetical reaction and think about the kinetics questions that we might ask. And so one might say, hey, what is the rate of this reaction anyway? Well, the rate of the reaction is the rate of appearance of products or disappearance of starting materials. And so we can express that as, say, the disappearance of a starting material as a function of time, or as the appearance of a product as a function of time. And, we can use anything, so it could be, the other product also, right? So we can measure concentrations of things. That's something that we can do, is measure concentration. And we can also measure time. You also probably remember that there are rate equations where we would say the rate is equal to some rate constant times the concentration of participants in the reaction, like starting materials. So AZ raised to some power, let's just call it X, and another starting material raised to some power Y. This is the form of a rate equation, and X and Y, these are orders, we say, and so the order of the reaction is X in AZ. The order of reaction is Y in B, and the order of the reaction overall is whatever X plus Y happens to be. There are also integrated rate equations, and you might recall those, where we can use them to determine something about what these exponents happen to be. But what we always can measure are concentrations as a function of time. And so the important thing to remember is that X and Y, whatever they are, they're related to something in organic chemistry, and that is to how the reaction happens. If that's true, then it would be really useful to be able to figure out what X and Y happens to be. So for example, we might observe that as we double the concentration of AZ, maybe there's no change in the rate of the reaction. Well, then X would be equal to 0. Or maybe there's a double in the rate of the reaction. Well, then X is 1. Or maybe it's quadruple the rate of the reaction. Well, then X is 2. And we could do the same thing for B, or for any other particular reactant that there might be in a reaction. So there's a relationship between the rate equation and these exponents and how reactions happen. And so we might want to do this kind of an experiment. This will tell us something about X. Okay, so let's imagine that there are two possible mechanisms. That's our hypothesis. So one of them, let's call it mechanism M. Mechanism M says, hey, here's AZ. It doesn't even need B minus. It just breaks down into A plus and Z minus. Then A plus sees B minus, and they get together and form AB. This is a two-step reaction. So here's step 1 and step 2. That would be a way to get the products that we observe in the reaction. We also might see that, hey, there's another possible mechanism. Maybe there's 20 possible mechanisms. We're just thinking about 2. And another possible mechanism might be that AZ and B minus both get together and they form the products. Okay, so this would be a one-step mechanism. So we got a one-step hypothesis and a two-step hypothesis. Okay, so how can we differentiate between these two mechanisms? This is where kinetics comes into play. So let's make an observation. So let's go ahead and do that experiment where we double the concentration of AZ. And we observe double AZ, well then we double the rate. Well, we know something now. We know that x is 1. We know that x is 1. Let's observe also that if we double the concentration of B minus, there's no rate change. We now know y. We know that y is 0, so that we know that the rate equation is equal to k times the concentration of AZ raised to the first power times the concentration of B minus, I'm including this for raised to the 0 power, okay, so which is of course equal to k times AZ raised to the first power. All right, so how do I determine which of these two mechanisms happens to be consistent with that rate equation? Well, if mechanism N is the mechanism, then I have two participants, AZ and B minus. In the step, in the rate determining step, there's only one step, so it is the rate determining step. There are two participants. If these are both participants, they would both have non-zero exponents. They would both have exponents of 1 in the rate equation. So this observation eliminates mechanism N. So the question now is whether or not mechanism M is consistent with this rate equation. So I want to explore these two steps. In step 1, a bond is breaking. That's unfavorable. It's the only thing that happens in step 1. It's unfavorable. That's hard. In the second step, I make a bond. It's the only thing that happens in the second step. That's favorable. That's easy. So if mechanism M were the mechanism, then the first step would be the rate determining step. If the first step is the rate determining step, what are the participants? The only participant is AZ. So the exponent on AZ in the rate equation would be 1. B is not a participant in the rate determining step for mechanism M. So its exponent would be 0. So this is consistent with our observed rate equation. So of the two, mechanism M is consistent with our experiment. Mechanism N is not. We have eliminated mechanism N. We have not eliminated mechanism M.